Okay, good morning, everyone. We'll continue on with our discussion of chapter 3, look at a few examples, and then, wrap up chapter 3 today. So, let me bring up our notebook, and let's go to the right section. Okay, so we stopped here last class. Let's go into the physical construction of the capacitor. Okay, capacitor, of course, is two parallel plates. So physical construction basically takes into account the cross-sectional area of the two plates separated by the distance or the thickness of that insulating material. And there is a constant in there, which is permittivity, noted by the Greek letter epsilon. And epsilon is given by E0 times ER. Epsilon 0 is the permittivity of vacuum. Epsilon R is the relative permittivity of the insulating material with respect to vacuum. Okay, and both of them are constants. If I ask this in a quiz or an exam, they will be provided to you. Okay, so you don't have to worry about memorizing anything. So they will be provided to you. A is the cross-sectional area. So area of either plate, it's actually not true. The only circumstances where this would actually be true is if both plates are exactly the same size and they overlap exactly the same points. If you have something like this, what area would you take? The overlap or section, right? Cross section right here. Because remember, capacitor, by its very fundamental description, is two parallel plates separated by an insulating material. So if there is no overlap, you don't have two plates. If you don't have two plates, then there's no capacitance. So it's only in the area of overlap where you have two plates, and that is the area that you have to take for capacitance. Okay, that is the area you have to take, area of the overlap. So again, doesn't matter what the dimension of the plate is, it's basically the area of that overlap, the cross section. All right, so it's epsilon A over D. And epsilon, of course, is given by epsilon 0 times epsilon R. Make sense? Good. Okay, so Q is equal to CV, as we saw in a previous equation, previous slide. Q, well, current, electric current is the rate of flow of charge, meaning dq over dt, the rate at which charge flows in a circuit. So if we take the derivative, we get the capacitor current I as C dV over dt. Same standard expression, similar to the one that we had for the inductor. I is equal to C dV over dt. And we can use the same notations, or same, not same notations, but the same manner of notations. IC would be C dVc over dt. And if we describe it as a function of time, we can write IC of t is equal to C dVc of t over dt. And we'll see that in the next slide. Okay, same. It's basically the exact same equation as an inductor, where in inductor you had V is equal to L di over dt. Here it's flipped. I is equal to C dV over dt. Right? So if we flip, sorry, not flip. One more thing. Good. All right. Okay. So if capacitor current is the derivative of the voltage, stands to reason if you apply a constant voltage, meaning it's a DC voltage, then the current would be equal to 0. Remember the first couple of slides of the capacitor, I explained how and why a capacitor current would go to 0, right? This is simply the mathematical expression. You keep in mind, we are not talking about the transient portion. Transient analysis comes in chapter 4. What we are saying here is what happens when the capacitor reaches full charge, right? So you apply DC voltage to a capacitor, it's going to start charging from 0 to whatever value of that voltage is. So then the value is still changing. But once it reaches steady state, once it reaches full charge, then the capacitor current goes to 0, right? And so we see that mathematically also. So if you apply a constant or a DC voltage to a capacitor, current will go to 0. So it acts like an open circuit. So steady state response for an inductor, what is an inductor? Opposite of the capacitor, right? So at steady state, inductor behaves like a short circuit, capacitor behaves like an open circuit. They are duals of each other, the exact opposites, right? Capacitor acts like an open circuit. So let's look at the equations. Same equations as what we saw for the inductor. If inductor voltage was given by the derivative of the current, L di over dt, the same is true for capacitor, except V and I are flipped. Capacitor current I is now given by C dV over dt. And here in these set of equations, we use both the subscript C as well as time. And again, it's the exact same thing as the inductor. Okay. The form of the VI equation, the form of the IV equation, the alternate equation is all exactly the same. If current is the derivative of the voltage, in order to find the current, we simply integrate the voltage and add up all the slices, right? You slice it up, dx, and you add up all the slices, you get the capacitor voltage VC. So you're not interested in the derivation as much as, well, students should understand what the equation represents, what it means, and what it is doing, and how to apply that equation. So let's take a look. First thing, the x simply represents the t, okay? I know it gets confusing to some students. I'll probably change it after the quarter, but that x is simply the variable. Remember how in the inductor I said if you have t and t, you have the variable also as t, and you have the limits of the integral also as t. And sometimes we do change the variable to either like x or y or a. More often than not, it's usually x. And so that's what I've done here. You simply change the variable to x because the limit of the integral is also t. Okay, that's the only reason. It doesn't have any other meaning beyond that. Okay, so having said that, this is again exact same equation as that what we had for the inductor. Since we are breaking it up into slices and we're adding up or we're summing up everything, we need a starting point and an end point. And that basically is represented by the limits of the integral minus infinity to t. The reason it's t is because we will first solve for the voltage or current as a function of time as t. Then if the limit is provided to us, we will enter those limits into that equation. Okay, so our answer, and you will see that in the example also, when we solve for the example, one of the examples, the limits are not given to us, so we simply solve for the answer as a function of time by plugging in this t. And then in another example, the limits are given to us. So we will first find the equation as a function of time, and then we plug the values of t into that equation. Okay. And so whenever we solve, we always solve it for a function of time. Now, minus infinity here simply represents all previous stored energy. Sorry about my writing. All previously stored energy in that inductor, meaning any voltage, sorry, not inductor, capacitor. Any voltage that is already present in that capacitor is being represented by that minus infinity, meaning all the time in the past, all the way up to the point at which we begin our analysis. Not variable, endpoint. And so we break that up into minus infinity to T0, where T0 is the beginning point, T is the end point. And minus infinity to T0 is representing all the previously stored energy that is present in that capacitor. And we can reduce that expression and call it VC, capacitor voltage at time T0. It simply accounts for the voltage that is present in that capacitor before we begin our analysis. Okay, before we begin our analysis. If the problem statement does not explicitly state any initial charge, you can assume it to be 0. Okay, so VC of T0 assume 0 volts if not explicitly stated. Often it will simply state capacitor has 2 volts across it. Now we apply a current or a voltage, calculate, such and such quantity. And so if it states it already has some voltage, then you simply add it as part of your equation or your solution. Otherwise, you can safely assume it to be 0. So most cases or most problems, we can safely ignore that quantity. So minus infinity to T0, meaning I'm beginning my analysis at this point. Everything else that was there before is basically just 0. I'm not concerned with that. All right, let's take a pause. Let me know if you have any questions. Any questions at all? Okay. So next we look at power and energy equations. Power is simply the product of the voltage and the current. Here I'm just using the notations PC of T. And so it's VC of T times IC of T. It's the same standard expression, P is equal to VI. You plug in the equation for the capacitor current, C dV over dt, and you obtain CV dV over dt. For an inductor, we obtained Li di over dt. Here it's CV dV over dt. And energy transferred is the rate of power transfer. So you simply add it up. So W is given by half CV square. Again, similar expression to the inductor. The inductor was half Li square. This is half CV square. Okay, half CV square. Now, you don't have to, I don't ask students to ever memorize any of the equations, okay? But you should be able to understand what the equations are, what they represent. At the end of this chapter, I have a summary slide, okay? At the end of the chapter, there is a summary slide. Oh, 7 right there. And that slide has all of the equations that you would ever need for this chapter. Inductor and capacitor, you have the primary equation for inductor, V is equal to L di over dt. Ci is dV over dt. Alternate equation, you simply integrate the quantities. Initial conditions, of course, I and V at T0. Steady state behavior. Behavior with a constant source simply means steady state behavior when you apply a DC source, either a DC voltage or a DC current. And of course, inductor behaves like a short circuit, capacitor behaves like an open circuit. Power equations, energy equation, and then we'll look at this in just a moment. How to add up capacitors in series and parallel. But again, this slide has all the equations that you would need. Again, memorizing is not something that I would harp on. If you can remember it, that's great. But you should be able to look at a problem statement, determine the right approach, determine which equations would fit the best, and be able to apply those equations. So it's more important to understand what those equations represent. Right? Make sense? Okay. All right, to add up capacitors and inductors in series and parallel, inductors add up the same way as resistors, capacitors the opposite. So if we have two or more inductors or two or more capacitors in a circuit, and if they are connected in a manner that is reducible, we can simplify our analysis. If you remember the quiz problem where you had two resistors in series on both sides, on the left and the right, and the hint I gave was you can reduce the circuit before you begin your analysis. So you reduce the two resistors to one, thus eliminating two nodes from the circuit. So now if you perform node voltage analysis, you have two less variables to worry about, right? So you simplified your analysis. The same manner, we can reduce the inductors and capacitors in a circuit. So if we have L1 and L2 in series, the same conditions apply for series and parallel, right? You have two components, they should be connected at a node. There should not be more than two components at that node. Then they are said to be in series. So LEQ would simply be L1 plus L2. If two inductors in parallel, then LEQ would be equal to L1, L2 and the reciprocal of that sum. Right? The same way as you would add up resistors. Keep in mind, you cannot add up capacitor to a resistance or capacitor to an inductance. They are separate quantities. They're physically separate, right? So you cannot add them up. But when we get to chapter 5, we will have impedances of all of these three components. And so there we can actually add those up. So if you have impedance for a capacitor and impedance for a inductor, we can add them up. Because impedance is the same quantity like resistance. Make sense? All right, capacitors, the exact opposite. So if you have C1, C2, you want to find CEQ. Well, CEQ is given by 1 over C1 plus 1 over C2 reciprocal. And if you have C1 and C2, CEQ will simply be C1 plus C2. Okay. C1 plus C2 if they are in parallel. And similar to resistors, it does not matter how many components we have in that series connection or in that parallel connection. Okay, you could have 1,000 components in series or parallel. As long as the conditions are satisfied, you can apply these equations. Let's see, 10:30. All right, any questions before we begin examples? Okay. So there are 4 examples. 2 of the examples use the VI equation. 2 of the other examples use the alternate VI equation or the IV equation. Okay. So in examples 1 and 3, we are given the voltage and we are asked to find the current. So we use the equation I is equal to C dV over dt, meaning you're trying to find the derivative of the voltage. In examples 2 and 4, we are given the current and we are asked to find the voltage, meaning we integrate the current. Right? So we're looking at both equations, basically all scenarios. The first 2, we are given the mathematical equation. The second 2 examples, I mean examples 3 and 4, we are given a graphical description of the quantity, and we will write the mathematical equation from the graphical description, and then we will apply our techniques. And so this is going to go a little bit fast. Oh, we have 30 minutes or so. One important note, all solved example methods use the capacitor as the component, but all 4 examples apply equally to inductors also. And I will show that for the first one. Okay, I will show that for the first one. So let's begin. We are given a capacitor of 5 microfarads, and we are told the voltage across that capacitor is 10 cos 6000 t. At this point, we're simply just doing math. Okay. Once we figure out which equation we need to apply, which is basically the entire problem setup, after that point, it's simply math. Okay. So we are given C, we are given the voltage, we are asked to find the current I. So we determine that we need to use the expression C dV over dt. Right? Voltage is given to us, we are asked to find the current. There's only one equation that fits that criteria, which is C dV over dt. So we simply need to take the derivative of the provided expression. Therefore, I of t is 5 microfarads, 10 raised to minus 6 times d by dt over 10 cos 6000 t. Derivative of cos is minus sign. We take the minus sign outside up front. We reduce the expression, and we should be able to get, what do we get? Minus 0.3 sine of 6000 t amps. Derivative of cos is minus sign, so we take the minus sign up front. Then we have 10 times 6000 multiplied with 5 into 10 raised to minus 6. Reduce the expression, and we get 0.3, or minus 0.3 rather, sine of 6000 t. And that's it. That's the answer. Okay. So note what I said earlier, or recall what I said earlier. I said oftentimes we may be provided with a value of the time. Whether we are provided with a value or not, we always solve for what is given to us. So in here, it is given to us that the voltage is a function of time. So time is a variable in that equation. So our answer will also be a function of time. Right? I as a function of time and t inside our expression. At that point, we don't care what value of t is. It's not given to us, so we won't worry about it. Voltage is given as a function of time, so our answer I of t also is a function of time, and we just leave it there. Does that make sense to everyone? Okay, so as I said, the setup of the problem is basically straightforward. You're given the voltage, asked to find I, determine the expression we need to use. From that point is math. Now, we are going to do examples 2, 3, and 4. I have in my detailed notes, my handwritten notes, so they are not like, some very super organized. But I'm going to post that on the web. So some students in the previous class, in the previous section, had some questions how I did the math. So I don't have that on the slides, but I do have it in my handwritten notes. So after class is over, I will scan them and I will, I will upload it on Canvas sometime today, hopefully. All right, any questions about this? Straightforward enough, right? So if the same question was applied to an inductor, the same question applied to an inductor would be L value is given, let's say 10 millihenry, and you were given the inductor current IL of t as 10 cos of 6000 t. Determine the voltage, right? Exact same problem. The only thing now we have flipped. Capacitor is now replaced with an inductor, and we are provided the current for the inductor, and we are asked to find the voltage. So if L is given to us, I is given to us, we set up the problem, and we immediately know that we can use the equation V is equal to L di over dt, right? Derivative of the current. And so it's the exact same thing as this. This value is immaterial. This value could be anything, as long as we understand what we need to do, right? And that's why I said right at the beginning that all solved examples apply equally to capacitors and inductors. Even though all examples use capacitors, the process, the procedure is exactly the same for inductors also. Is everyone clear on that? Okay, so it does not really matter what you're given. Okay, I'm covering all 4 scenarios right there. Okay. All right, let's take a look at example 2. Example 2, we are given the capacitance value, 2 microfarads. We are given I of t, and now we are asked to find voltage. So what do we do? There's only one other equation that we can use, right? We are given the current, so we need to integrate that current between the time intervals and find the answer for the capacitor voltage. Once again, note that we are not given the time interval. We're not given a specific time interval. We are simply given the expression for I of t. The value of t is not given to us. So our answer will also be as a function of time. We won't worry about the value of time at all. Make sense to everyone? Yes? Okay. So C is 2 microfarads. I of t is given to us. We will use the expression V of t is the integral of the current. And the limits, well, this one goes from t0 to t. We can change this to ix dx. Right now, I'm not doing so. Okay, this can be changed to ix and dx. This is the variable, that's the limit. And then, of course, we need to add the voltage at time t equal to 0. And what is that voltage? Anyone? 0. It's not given to us. If it says that an initially charged if a 2 microfarad capacitor was initially charged like 2 volts, then we would take that as VC at T0 and we would add it in there. It's not given to us. Simply take it to 0. This is 0 volts. Every time a truck goes by, I always think it's going to come crashing through the window. That's just too much of an angle. Sorry, I didn't mean to scare anyone in the back. Okay, All right, so V of t, we got 0 to t or t0 to t. We plug in our values. Capacitor is 2 microfarads. 2 microfarads. T0 is 0. Endpoint is t, which is basically, it's just an unknown variable. We don't really care. And we simply plug in 6 into e raised to minus 3000 t dot dt. Each slice. All right. And then one more thing is that, well, instead of me telling you, why don't you tell me? What else is missing in there? One quantity. This is where being detail oriented is a requirement in an engineer. Milliamps. We gotta have 10 raised to minus 3 in there. -10 to -3. That's it. And we solve for that. And at the end, a limit for the integral, of course, is 0 to t. Well, actually, let's plug it this way. T to 0. This is e raised to ax, right? E raised to ax. So we take that out. Also solve for t squared over t. Plug in limits t0 to t, you get e raised to minus, well, actually, because it's minus 3000 t, you have a minus in front. You plug in the limits, you get e raised to minus 3000 t minus e raised to 0. It's not O, that is 0. So final answer comes up to be 1 minus e raised to minus 3000 t. And ends up being volts. So if I hadn't entered the 10 raised to minus 3 in there, my answer would have been incorrect. Instead of being volts, answer would have come out to be millivolts. Does the process make sense? Okay, leave the maths on the side for just, for a moment, but think about the process, right? As engineers in your own field, you'll use the same math over and over again, right? That's why we take calculus, but the process is what is new. So again, I is given to us. We are asked to find voltage. We determine that the equation we need to use is V is equal to 1 over C integral of the current. The current is being integrated or summed up over the time period minus infinity all the way to t. T is the end point, but it is not specifically given to us in the problem itself, right? So we don't really care about it. We just find our answer as a function of t. That's all we are doing. Initial voltage is not given to us, and so we just assume it to be 0. So minus infinity to the beginning point of our analysis at t0 is 0. And then we simply find the function from t0, which is basically 0, all the way to t. Did all of that make sense? Hopefully. Okay, so we looked at 2 examples. The first example, we were given the voltage, we find the current. Second example, we were given the current, we find the voltage. Both of those examples can be flipped and applied equally to an inductor also. Okay, the same way that we applied an inductor for that first problem, we can do it for the second one also. I'm not going to show it to you again. It's not just possible to do everything in 50 minutes. But if you're given the inductor current, if you're given the inductor voltage and you're asked to find the inductor current, use the exact same equation, right? IL of t is now 1 over L integral of the voltage. The second VI equation. Does that make sense? Okay. All right, it's 10:46, so let's move on. Well, let's take 10 seconds. If anyone has questions, please ask. Any questions at all? Okay, no questions? So what do we have here? We have a graphical description of a voltage, right? Graphical description of a voltage. We are given a capacitor value as 5 microfarads. And that function has a non-linear relationship with time. If we look at the function, x-axis is always time. If we look at the function, we can see that before 0 and after 8, the value of that function is 0. So we don't need to worry about that function before 0 and after 8. Okay. Because it has a nonlinear relationship and we need to describe that function in terms of a mathematical equation, we will break up that function into different pieces. And the reason we break it up is so that we can have a linear, so that each piece can have a linear relationship with time. So we break it up right here into 2 parts, from 0 to 6 and 6 to 8. And each piece is linear with respect to time. So we are able to write a mathematical expression for that piece and solve using our equations. And hence the term piecewise linear analysis. Okay, this is something you may have encountered in your own fields, perhaps. Okay, it's not just in electrical engineering. If you have not, maybe you would sometime in the future. Anyway, does everyone understand what I'm trying to convey? Right? We are taking a nonlinear function, breaking it up into individual pieces so that each piece has a linear relationship. The purpose is to allow us or enable us to write an equation for each linear piece. Once we have a mathematical equation, we simply solve it how we solved example 1 and example 2. Okay, so this is similar to example 1 in the sense that the voltage is given to us and we want to find the current. Example 4, we are given the current and we want to find the voltage. All right, so let's begin. And we'll use simple techniques that we have learned in the past, like slope line intercept method, to write an equation for the line. That's all we are going to do. So T can be broken up into 2 parts, T1 and T2. And T1 is going to be 0 to 6 milliseconds. And T2 is going to be 6 to 8 milliseconds. For T1, my X1, Y1 is 0, 0. X2, Y2 is 6 milliseconds, so 0.006 and 24 volts. So my slope is 24 minus 0 and it's 0. This comes out to be 4,000 volts per second. Right, 6 4 20 by 0.10 minus 3, 4,000 volts per second. Y-intercept is 0, so Y is equal to mx plus b. Y is voltage, right? Voltage is on the y-axis. So V of t is 4,000. X is t. X-axis is t. So 4,000 t. Y-intercept is 0. And that's the equation for the time period between 0 and 6. So we break up this T1, this becomes T2. Once we break it up, we are able to write a mathematical expression. Once we have a mathematical expression, we can use our standard equations I is equal to C dV over dt, and simply solve for the current. Similar to example 1. Does that make sense? Okay. The only thing that is different here is basically breaking up the time period and and generating the equation. In examples 1 and 2, the equation was already given to us. Okay, here we have to derive the equations ourselves. Okay. Let's see how we doing on time. 10:52. Okay, so from this point on, IC of t is same, C dVc over dt. You plug in the values. C is what? 5 microfarads, so 5 into 10 raised to minus 6 to d by dt of 4000 t. We solve that, and we get this 20 milliamps. Okay, 20 milliamps. The second portion for T2, X1, Y1 is going to be 0.006 and 24. X2, Y2 is 0.008 and 0. So slope M2, let's call this M1. Slope M2 is going to be 0 minus 24. And I get minus 12,000 volts per second. And y-intercept will come out to be was 24 volts for every 2 milliseconds, so 4, 6, so 48 here, and 96 here. The equation of my line would be V of t is minus 12,000 t plus 96. You plug the same thing, same value into this equation, and we should obtain minus 0.06. Let's write it out. C is what? 5 microfarads. D by dt minus 12,000 t plus 96. Solve that, come out to be minus 0.06 amps or 60 milliamps, minus 60 milliamps. Okay, if you plot both of those, it's a constant value. This is 0.02 amps. The constant value of 20 milliamps. And the other side, it's minus 60 milliamps. Okay, questions? Any questions at all? Yes. Which values? Capacitor values, component values? Yeah, component values. Yeah. So essentially, as I said, all 4 problems are similar in the sense that we determine which quantity is given to us, whether voltage is given or current is given, and then look at what component it is. Then from there, we determine what equations we need to use. In the first 2 problems, the equation were given to us, so we didn't have to generate them. in problems 3 and 4, the equations are not given, the graphical descriptions are given. So everything that you need, all the information, would be in that graphical description. The time, meaning on the x-axis, the time interval, as well as the value of the function on the y-axis. And so it would be your job, or as part of the assessment, whether students can actually extract that information from a graphical description. That makes sense to everyone, right? Okay, I have 3, 4, well, 4, now it's 3 minutes. 3 minutes remaining. If you have to leave at 11, free to leave. I will continue on for a couple more minutes and wrap up the last example. Quiz on Monday based on chapter 3. Your homework should also be, well, I'm not sure when it's, I think I moved it back to Sunday. So that should be there. I mean, it should be there on Canvas. Okay, so last example, example 4, we are given graphical description of the current. Capacitor current is given to us. Capacitor value is given as 4 microfarads. We are asked to find the voltage. So this is similar to example 2, where we need to integrate the current to find the voltage, right? To integrate the current, again, we use the standard same expression, but here again, this is an example of a piecewise linear analysis. The entire function has a non-linear relationship with time. However, we break it up into individual pieces, and each individual piece has a linear relationship. So if we break it up into 2 pieces, we say T1 can be from 0 to 2 milliseconds, and T2 would be from 2 to 4 milliseconds. So if it's, let's look at T2 first. If you look at T2 first, it's a straight line, meaning it's a constant, right? It's a constant. So we don't need to describe it with any mathematical equation. It simply has a value. And it's not shown here, but it intersects at -8. And here, this value is 16. So 16 microamps and -8 microamps. And so hence, we can write I of t simply has a value of -8 microamps for the second time period. Make sense? Right? For the first one, T1, we do the same thing as we did for example 3. We find the slope first, and then we write the expression for the line. So in this case, the slope is going to be x1, y1 is 0, 0. x2, y2 is, what do we have? 2 milliseconds, so 0.02. And we have 16 microamps. So 16 into 10 raised to -6. Okay. And so slope simply be here, 16 micro divided by 2 milli times t, and x-axis is of course 0. Okay, so this is the slope of the line m1 and m1 times t. Does that make sense? I know I'm going a little bit fast, but hopefully students can review the video. Right, we just find the coordinates, the endpoints of the line, write the equation of the line. Apply it to our standard expression. 1 over c integral from 0 to t, I of t times dt. Here the variable is changed. The x has no meaning beyond the change in variable. That's all. Okay, ix dx. Plug in the values. Capacitor is 4 microfarads. Expression for 0 to 2. 8 into 10 raised to -3. Integral t. You solve it and you plug in the limits 0 to t. So you get t squared times 10 cubed. So 10,000, sorry, not 10,000, 1,000 t squared. Okay, 1,000 t squared. Now, here's the thing that I wanted to point out. That's for the first time interval. That's math. Okay, we'll look at the math I'll post it on Canvas. You can look at the steps. And again, all engineering students, I would expect that you'll be able to solve integration and integrals and derivatives. But here's the important thing. When we get to the second time period, what do we have? Second time period, T2, my initial beginning point of analysis is 2 milliseconds. And end point T is 4 milliseconds. Right? It's a constant, so I don't have to actually write an expression. It's simply 8 microamps, right? 8 microamps, constant. So no equation for the line. The equation for the line is 8 microamps. I solve that, and then my limits of integration are 2 milliseconds to t. Now, I'm solving as a function of time, so I'm not plugging in 4 right now. I want my answer to be as a function of time. And that's why I still keep the final limit as t. Okay, so I obtain my answer as a function of time. So t is in there. Importantly, beginning point is 2 milliseconds. Beginning point is 2 milliseconds, but I have to add up the energy that was present at 2 milliseconds. So I go back to my first time period, T1, and I calculate voltage at 2 milliseconds. So I plug in 2 milliseconds in that equation, and I calculate that to be 4 millivolts. Then I carry that 4 millivolts and add it to T2. And that's where that 4 millivolts comes from. This is VC T0, meaning VC at 2 milliseconds. Okay. So I know we are rushed. It's already 4 minutes and there's a next class waiting. So I'm going to end class here today. I'll see you all on Monday. I will be available all weekend long. I don't have any big plans on Sunday except watching the game. If you need to see me, send me an email. I'll be happy to see you over Zoom. All right. Have a good weekend, and I will see you all on Monday. Me? No. I don't have any skin in the game. My teams are the Vikings and the Ravens, which, well, so I went to Louisville, grad school. So I saw Lamar Jackson. So I'm a big